Hi there, I am Ritojit Kundu, a PhD student at IIT Kanpur. So I'll be one of your tutors in this course, Advanced Quantum Mechanics with Application. So today I'm going to talk about week 0 assignment. Uh, so this is very simple, but this is mostly prerequisite material. But you have to go through this because much more complicated stuff will be coming in this course later on. This is the week 0 assignment. So I have solved the problems and I'll discuss them as we go along. Okay, so the first question asks to find the commutational relation x comma p, where x and p are position and momentum operators in quantum mechanics. So to start with, we'll write out the momentum operator, which is minus I h bar del x, and you have to remember that x comma p, this commutator bracket, is also an operator. And this, because this is an operator acts on any states. So let's say this acts on a arbitrary state psi x. Okay, so now in the next step, let's just expand out the commutator bracket, and the commutator bracket, let's focus on this term. Okay, so you see in the next step I have replaced p with I h bar del x, and a minus and minus got cancelled and become plus. Now this del x operator acts on this product x times psi x, and we will be using product rule of this partial derivative to simplify this term. So now so if we just expand this out, we'll see that okay, we get psi of x times I h bar, and there is additional I h bar del x. So this operator is nothing but p operator with a minus sign. So we see that the first and the last term actually cancels, and we are only left with I h bar psi x. So our relation becomes simplified to this. Okay, now in the beginning I assume that the psi x is any state. Okay, so if this relation is valid for any arbitrary state, then this is just an identity. So the operator x comma p commutator is just nothing but I h bar. Okay, so let's move on to the next one. So now this asks to use the result of problem 1 to compute x comma h, where the h is the Hamiltonian for a free particle. Okay, so you might be aware that for a free particle h, the Hamiltonian is given by p square by 2m, where p is the momentum of the particle and m is the mass of the particle. And we'll be using the identity that we can take a commutator bracket a comma b c, and this simplifies to a comma b times c and b times a comma c. Okay, so to simplify this, we just write these operators down, x comma p square by m, and we use the aforementioned identity. So we get out p from here and p in this side, and there is a 1 by 2m. This is just a number, so we just take it out of the whole expression. So here you see that there is there is x comma p commutator that we just calculated, and this appears twice in this equation. So for those, we will just replace with I h bar. Okay, and because I h bar is just a number, we will just get it out, and we will have this. Okay, so this commutator has a very deep relation with a Poisson bracket. This is a side remark, but I mean, this is a good thing to know. So one can directly write for the rules of quantum mechanics by just transforming a Poisson bracket to a commutator bracket by I h bar. So you can probably think about it. Yeah. Okay, so the next problem is, it asks to write down the dispersion relation for a free particle, right? So for a free particle, the energy, you know, is p square by 2m. Okay, and this is a momentum. Okay, now we want to replace the momentum in terms of the wave vectors. Okay, so the relation we'll be using is p is equal to h bar k, where this where this h bar is the Planck's constant and k is the wave vector. Okay, so when we'll use this p, and we will replace inside this expression. So that will give us h bar square, 2m and ek. So now in this form of this expression, we have actually written the energy in terms of the wave vector. So when we write an energy in terms of wave vector, that is actually called a dispersion relation. Okay. Okay, so the next one is write down the expression for group and phase velocity. So from, let's say, wave mechanics, from classical wave optics or wave and oscillations, we know that the group velocity is just a derivative of omega with respect to k. So you know that Vg is del omega del k. Okay, but you see that this omega is frequency, but energy, so energy has the dimension of h bar times frequency, right? So to the match the dimension, there is an additional 1 by h bar which is used here. So now we'll be plugging in the ek and del k, right? So then the phase velocity, okay, so we can plug in the free particles dispersion in this case, and so we'll get the group velocity to be h bar k by m. Okay, and the phase velocity is even simpler. It is just the dispersion divided by the momentum. So here it becomes h bar k by 2m. So you can see that this group velocity and the phase velocity, there is a very nice relation, that the ratio of the aforementioned 2 is just 2. Okay, so let's move on to the next one. So now in question 5, you have to write down the energy expression for a particle in one-dimensional box of width a. Okay, so we have solved a particle in the box. So this is the first example of quantum mechanics that you do, and you can directly write away the expression for the energy, which is nothing but n square pi square h bar square by 2ml square. So L is the length of this of the 1D box, and m is the particle which resides inside that box. Okay, and n is the corresponding quantum number. Okay, so here we are writing this exactly. Okay, so to write this thing, we have to solve the time independent Schrodinger equation, okay, which is given by this expression, and then we also have to match the boundary conditions at x is equal to 0 and x is equal to L. Okay, so then after doing that, after all doing all these steps, this gives you the condition that the energy will be of this form. Okay, but there is another alternative and enlightening way, which I'll be demonstrating to you. Okay, so just to remind you, infinite this particle in the box means that v is infinity when the position is outside the box. Okay, and so psi x will be 0, as there is no probability outside the box, right? So particle cannot go outside the box because there is infinite potential, and so that means that the wave function has to continuously go to 0 at some point. So this is the boundary where it will become 0. Okay, so the wave function has to obey this boundary condition, that wave function at 0 x is equal to 0 is 0, and wave function at x is equal to L is also 0, or L or A. Okay, so only so wave functions which has nodes on these 2 points are allowed. Okay, so you can think about what kind of wave functions you can have. Okay, the very simple solution is just a sine kx, right? So I can have a sine kx, but the k is has to be some particular form, okay, to be the solution of particle this problem. So at x is equal to 0, we know that sine kx becomes 0, and at x is equal to a, psi at a also becomes 0. Okay, so this actually gives a condition on k, that k can only be multiple of pi. Okay, so now we can solve for k, and we know that the dispersion is nothing but h bar square k square by 2m. So we'll just plug in this part to a, yeah, to m. So we'll just plug in this momentum inside here. Okay, and you will see, you will find this thing. So this is nothing new, but this is another kind of approach to get the eigenspectrum of your regular particle 1D in the box. Okay, so in the next problem, you are supposed to write down all the degenerate wave functions for a particle in two-dimensional box contained in 0 to a in x direction, and also 0 to a in y direction. Okay, so so that the energy becomes 50 times times pi h bar square by 2m square. Okay, So as you know that the particle in a 2D box has dispersion like this. So n square plus m square times this quantity. So you have to find nm so that my energy becomes something like this. Okay, so so these constants they cancel from both of the sides, and you have to find the solutions there, so that the n square plus m square is equal to 50. Okay, so you can write down all of the integers that you can think of, so that will make up this 50. So here I can only find 3, so which is 1 7. So 1 plus 7 square, which is 49, gives you 50. 5 square plus 5 square, 25 plus 25 gives you 50, and 7 square, 49 plus 1, that also gives you 50. So these are the three possible states that can give you this energy 50. Okay, and the corresponding wave functions will have two sign parts. Okay, so sine n pi, so for one for the x part, one for the y part, and so you can go ahead and directly substitute m and n in this in place of this symbols. Okay, and those will be your wave functions. Okay. Okay, so write down the Heisenberg equation of motion of operator O. Okay, so the Heisenberg operator, the definition of Heisenberg operator is given by, so there is a O which is sandwiched between e to the power I h t and e to the power minus I h t, where h is a Hamiltonian. Okay, so let's say you do not know what Heisenberg's equation of motion is, but you know that this is some this tells about the time dependence of an operator. Okay, so let's you start with this and you take a time derivative of this operator. So what will happen, the ddt will act on all of this, and it is like a product rule, so it will act at one of this one at each at one time. Okay, so the ddt will first act on e to the power I h t. So 1 e to the power 1 I h t goes out of this, then we are left with e to the power I h t o e to the minus I h t. Then on the second turn it will act on this part, e to the power I minus I h t. So that will also give h e to the power minus h t. Okay, so you see that so then we can actually combine this part. Okay, we can combine this part, and this is nothing but our OT, and we can also bring this back here, because h and e to the power minus h, they commute. Okay, so then next step it becomes OT. So you have brought it here and becomes OT, then this becomes just a commutator. So you just so I have just brought I here, there is a minus to compensate that I have changed the commutator. Okay, so so this is the Heisenberg's equation of motion. Yeah, so this is what you are asked to find out. Okay, so okay, so the next question is, write down the three Pauli matrices for S is equal to half particle. For S is equal to half particle, so there are these three sigma matrices. Okay, so the three sigma matrices are sigma x, sigma y, and sigma z. Sigma z and sigma x, these are real valued, and sigma y has some complex entries. Okay, so for any other arbitrary spin S, there will be actually 2s plus one dimensional matrices. Okay, Pauli matrices. Okay, okay, so now this is interesting. Obtain the operator form of x in the momentum representation. So so let's first start with writing the eigenvalue equation of this x operator. So when x acts on a wave function, now this gives the position back, which is here a number, and the wave function, right? So on the left hand side, the x is just an operator, and on the right hand side it is just a value. Okay, just a number. So now let's assume that the Fourier transform of psi x is given by phi of p, which is formally written like this. So psi x is 1 by square root 2 pi and minus infinity plus infinity phi k e to the power I k x dk, and phi k on the other hand is similarly is defined by the inverse Fourier transform. Okay, so okay, so now let's think about this object x times psi of x, and we can actually do a Fourier transform of this whole equation. Okay, so if we'll do that, so so this comes inside the integrand, and we see that if we will take a derivative of k of only this part, we will get a x. Okay, so to compensate the I, I have also put an I here. Now this integration doesn't depend, the integration variable is x, so I can easily pull this part out of this integration. Okay, and then I am left with psi x e to the I k x, and you can recognize that this is nothing but the momentum wave function. Okay, momentum represented wave function. So so we see that if you do a Fourier transform of x times psi x, then it becomes just minus I del k. So from this we conclude that if you do a Fourier transform of x, then that becomes an operator like minus I del k in the momentum space or in the wave vector space. Okay, all right. So yeah, this is this asks you to write down the Hamiltonian for a simple harmonic oscillator in both position and momentum representation. So as you know, in momentum representation, in position representation, it is given by p square by 2m. So I have written out the p square by 2m part in terms of this partial derivatives, and there is a quadratic potential, okay, for in harmonic oscillator. So just before this question, we have explored the transformation rules from position to momentum space. That means that if we have momentum, if we have x or x, then it becomes minus I h bar del p. Now if we have minus del x, it becomes just p. Okay, now we'll be using this, and we'll be just substituting this and use this in our Hamiltonian. So we'll find out that what are the momentum, what is the form of the Hamiltonian. So we see that upon substitution of this momentum and position, you see that this exactly looks like the similar operator, so which has like a second order derivative but with respect to p, and which is a polynomial but with respect to p. Okay, so it is quadratic with respect to p, but the coefficients are now changed. Okay, so you can go ahead and you can also write down the solutions, okay, just by identifying that this is nothing but the just harmonic oscillators equation in the real space, where the factors are a little bit different from the previous case. Okay, so okay, so this is the last one for this session. So they are asking you to write down the expectation value of an arbitrary operator O in terms of density matrix. Okay, so so to write in terms of density matrix, this is the rule is that it is just a trace of rho times O by divided by rho. Okay, so you can understand this thing in a simplified manner, that the rho operator is just psi and psi outer product, and if you just write psi and O and take a trace over it, this becomes nothing but psi O psi. Okay, so this is nothing but your normal expectation values, and this trace of rho is done to make sure that okay, this to take account of the normalization. Okay, so this was mostly the dry run or the week 0 video, and next time we'll have the week 1 discussion also. Okay, so that will be it, and I'll meet you next week.